Thank you.
Okay. So what we therefore use in SRAMs is this 6 transistor cell. Over here, what has been done is, this inverter is there, this inverter is there, then this clock transistor has been taken up, and this clock is now called word line. Okay, and this D transistor has been removed and put in a common area which is called the IO region. You remember I said there is a right driver where D would come. So this transistor, the D NMOS has been put in the right driver now. So what has happened is that what you are repeating millions of times in a storage memory is not these 14 transistors, but only these 6. And you have a 60 memory cell. So this word line is nothing but the clock. This is the inverter that we talked about, where we said that these PMOSs have been removed. And these bit lines actually represent the internal nodes over here. This node. Such that the data, the NMOSs of the data are in the right driver down below. Are you able to see this? That a 60 memory cell is a minimized latch, nothing else. Any questions? Okay, great. So now how do you read and write into this latch? So to be able to read into this latch, what you do is you first pre-charge the bit lines. So these are bit lines and bit line bars. You pre-charge them and you take word line to be high. When this particular set of NMOSs are turned on because word line went high, what happens? They start to connect bit lines and the internal nodes. This side stores a 0 and this side you pre-charge to VDD. What will happen? Some current flow would happen. As that current flows, bit line would discharge BL bar, because this is also 1 and this is also 1. BL bar would not change. And it is this differential that is created that you will sense at the sense amplifier to complete the read operation. Are you able to see this? Any questions?
Sir, please explain the working again, sir.
Okay. So what are we saying is that even before you select the word line, you pre-charge, you maintain the bit lines at a particular value. So these bit lines are, as we just shared, internal nodes. They are simply capacitors. So you pre-charge them to a particular value. And then when you turn the word line on, the side on which 0 was stored, that particular side, the bit line would discharge. So one of the bit line remains as VDD because on that side 1 was written. The other bit line starts to fall from the 1 level. And you measure the differential generated, and that is how you say, okay, I'm storing a 0 or a 1 inside this memory cell. So if BL discharges, you say it is a 0. If BLB discharges, you say it is a 1, or vice versa. Okay?
Yes.
Is this clear now?
Yes, sir. I understood, sir, but why are we exactly discharging this BL, sir? I mean, what's the exact...
Otherwise, how will you make out what is written inside the memory cell?
Oh, yes, sir.
You want to read, no?
Yes, sir. Understood. Yeah.
So this is a read operation. Okay. So now how do we write into the memory cell? Let's say in the same memory cell where 0 was written on the BLTI node. Now, if I want to write a different data, what it means is that BLTI should go to 1 and BLFI should go to 0. Now, what would you do? See, you have this NMOS, which would connect bit lines to the internal node. what would you do? You want to write a 0 and you want to write a 1. What would you write on the bit line? Hello?
Sorry, sir. Can you please
Charge
repeat?
of the bit line.
I'm asking you, see, in the read operation, we pre-charged both the bit lines to 1. Then we said, okay, the side which stores a 0, that will discharge the bit line and we will know whether it is a 0 or a 1.
Yes, sir.
Now I want to write inside the memory.
Yes.
And I have those NMOS pass gates.
Yes.
What would I write on the bit line now to be able to do a complete write inside the memory?
Sir, we'll set the bit line. So if you want to write a 1, we'll set the bit line high by the right driver and we'll turn on the word line so that this is right on the
Okay. What about bit line bar?
yeah, bit line bar will be the complement of bit line, which will be written.
Okay. So in the read cycle, both bit line and bit line bar were written to 1. However,
Yes.
in the write cycle, you will put them at a value which is desired. For example, if you want to write a 1 on particular bit line on a particular side, you would maintain that bit line to be 1, and the other bit line side, you will put a 0. And then what happens? Look at it. See, NMOS will transfer 0 much more efficiently than a 1. So what happens is, when you take the word line high, after keeping one of the bit lines to 0, the node 1 discharges fast. On the other side, the node 0 will only charge up just a little because it is an NMOS, through an NMOS. Once node 1 has completely discharged, that is when, like, you see this PMOS turns on. And that is when the write operation is completed. So initially, there is only some charge that can come from the bit line. It cannot really take 0 to 1. Unless this comes into picture, you will see your write operation cannot complete. You will never be able to go to full VDD unless you have PMOS coming into picture there.
So can we say that writing 1 would take more time than writing 0? Like, as you have just explained.
Very good. Very, very good. This is what it will take. Because to be able to write a 1, you first need to write a 0, and then only 1 will be written. Otherwise, 1
Yes.
cannot even be written. Very good. Any questions about the write operation? Great. So this is how we would do the read and write inside the memory. And then for the memory cells, we have multiple figures of merit. See, just थोड़ी देर पहले we looked at the figures of merit for a memory. We looked at speed, power, area, refresh, endurance, so many things. There are many figures of merit linked to Bitcell also. For example, cell current. Cell current is a figure of merit that tells how quickly my bit line will discharge during the read operation. So it will control read speed. Bitline leakage is about power and to some extent also about read speed. Cell stability. So what happens? See, so cell current, let's just quickly go through the figures of merit. Cell current is about, as I said, speed, the speed at which the bit lines can discharge. And it is essentially determined by the stack, the sizing of this stack. The bigger the devices, the more current there would be. But realize, the bigger these devices, more is the leakage also. More is the capacitance of the bit line also. So we cannot simply keep on increasing the size. Cell stability is one of the most important specifications of any storage element, whether it is a flip-flop or a latch or a memory cell. And the challenge is highest during read operation, because during read operation, you expose your latch, your storage element, to external noise. What happens is that when you start a read operation, current starts to flow like this. When a current flows, see, this was initially storing a 0, But to ensure that a current flows, this value will go from 0 to Vx, a value higher than 0. Otherwise, there would be no current flow. And as this goes to a level higher than Vx, a level higher than 0, it can actually turn on the devices on this side, turn off the PMOS on this side, and so on. Okay, and that is where risk starts to appear. So the cell stability starts to degrade. You wish to ensure that this Vx is as low as possible. Therefore, we get another sizing constraint over here, which is that pass gate has to be much more resistive than the pull down. So this is the pass gate. This is the pull down. The pass gate has to be much more resistive than the pull down. If pull down is more resistive, then what happens? This node will rise above VDD by 2, and it will kind of flip the contents of the memory cell. We don't want that to happen. So there was this question, na, ki if we remove those PMOSs, what happens? So we already start to see that there are sizing constraints that would come. Otherwise, the memory cell operation will start to get hampered. Are you able to see this? Any questions? Okay. So the next figure of merit that we are concerned about is write margin. Write margin essentially means that, see, what are we trying to do? We said that this bit line would go to 0, and then this internal node will discharge. So can you really discharge a capacitor to 0? See, what is this? A bit line is a RC. This is a wire, so which it would have some R, and the wire also has some capacitance. If I apply a voltage source here or a current source here, how long do you think it will take to discharge this particular capacitance to 0? How long? You realize that it being an RC circuit, it will take a huge amount of time to discharge the capacitor to 0. Are you able to see this? Okay, let us wait until you see this.
Yes, sir. It's first order differential equation. So it takes infinite, practically according to the equation, it takes infinite amount of time to discharge the whole thing.
Now, do you have that kind of time when you want to read or write a memory? No, you want to operate your memory at 1 gigahertz. So what happens? You say that, oh, I cannot really discharge my bit line to 0. What is the highest level of bit line at which I will still be able to write into the memory cell? Is it 50 millivolts that I discharge only up to 50 millivolts and I will still be able to write? Or is it 100 millivolts? And you will realize that as you have a better write margin, you can actually operate much faster because you do not really need to go through all those RC delays now. Instead of 6 RC, you can go at 5 RC and still be able to write inside the memory. Are you able to see this? So write margin is also a metric of speed. It is a metric of writability, whether I can actually write into the memory cell at all or not. And in the course, when we look at it, we'll also look at the advanced technologies where write margin is actually negative. What it means is you need to take bit line at a voltage which is lower than 0 to be able to write into the memory cell. And we will talk about negative bit line write assist schemes in the course. Okay. So when you want to write into the memory, you want to say that this improve the write margin. You need to say that this pull up should not be able to drive or should drive lesser current than what this stack of pass gate and write driver can sync through it. Are you able to see this? That the series of pass gate and write driver has to be stronger than the pull up. Are you able to see this constraint?
Yes, sir. Yes, sir.
Okay. So here, do you realize now that we're talking about size of pass gate, pull down, and in this particular case, we are also brought in the pull up, the PMOS into picture there. And if we know all these three sets of constraints, you will realize that designing the memory cell, even though it is only 6 transistors, is not a simple task. That is why we have numerous people working on optimizing the memory cell for the densest memory or for highest speed memory and so on. Okay. Leakage is a part of power consumption. All off devices in a Bitcell leak. On devices also have junction leakage. There is gate leakage also. So to have low leakage, you want to use as small devices as possible so that junction leakage is minimized. Gate leakage is minimized. So you want to use as small devices as is possible to reduce leakage. You can also use long channel devices. So typically in industrial SRAM cell, you will notice that if the minimum channel length allowed by a technology is, let us say, X, then the length that is used inside the memory cell would almost always be more than 10 or 20% more than this X. It will be 1.2x or 1.3x also at times. Okay, so the length of memory cell transistors is always larger than the minimum length, so that you can reduce the leakage there. Okay, and you will find in some papers that people also talk about using thick gate oxides so that you can reduce gate leakage. In how do I put it? In the high K metal gate technologies, the requirement of thick gate oxide usage has reduced a bit, but even then, even for a high K metal gate stack, if you use a thick gate oxide, you can reduce leakage a bit because of reduced paneling. Okay. Any questions still here? Because now I'm coming to the concept of butterfly curve. Have you heard about a butterfly curve in reference to a latch? What is a butterfly curve? Any idea? Okay. So let us say we just have 2 inverters over here. You see this switch is open. So we do not have a latch. We just have 2 inverters. In 1, in 2, and out 2 are the 3 nodes that we are talking about over here. If we look at the transfer characteristics of the 2 inverters, what do we see? That as in 1 rises, in 2 would fall. Then as in 2 rises, out 2 would fall. Are you with me on this? These are the transfer characteristics of these 2 inverters. Is that clear? Any questions still here? Okay. So what do? We say memory cell we have to find the stability of a memory cell. In a memory cell, there are these 2 inverters are connected back to back. So what we do is we close the switch. As soon as we close the switch, now in 1 is no longer connected. However, that in 1 is replaced by out 2. So as out 2 rises, in 2 falls. The other curve was already between out 2 and in 2. Now realize that we are talking about, for this circuit, we're talking about 2 curves that relate out 2 and in 2. And if I merge them one over the other, what would happen? They would simply come one over another, and what you would have is a butterfly curve. So this latch is characterized by the transfer function of this latch is a butterfly curve. Are you able to see this?
Yes, sir.
So now what is important to realize is how much noise can I put in there? That is what is meant by cell stability, na? That how much noise can I be immune to? The more noise I'm able to handle, the more stable the cell is, more stable the latch is. So now let us go to another level of abstraction. We say that this latch, if I am storing a 0 on one side and 1 on the other, the worst case noise that I need to inject is 0 going towards 1 and 1 being reduced and going towards 0. That is the worst case noise pair that I can inject on this particular latch. Are you with me?
Yes,
Is this
sir.
the right assumption? This is the worst case for the latch for noise injection? So now, is it okay if I say that this latch is essentially a long chain of inverters which are storing 0, 1, 0, 1, 0, 1, 0, 1? Can I say it like that?
So why?
Where N1 is equal to N3 is equal to N5, they're all connected. So there is this loop. See, I give a small noise here. This noise can get increased over here. Then out 2 would increase that noise further. So this small noise has increased and it is now fed back into this inverter.
Okay, so
Now,
noise is amplifying. Is it that?
I'm sorry?
So noise is amplifying itself.
You can amplify, no?
Yes, sir. Yes, sir.
A latch is amplifying action, is it not?
Yeah.
That is how you write into a latch. So latch
Yes,
can
yes.
amplify. Now, ab kya ho raha hai? If I just keep one picture, then I am not able to overlap this big noise and small noise. However, this big noise will actually go to this inverter now and will cause much more havoc. Is it not? So just to make my work simple, what I'm trying to do is I'm just opening this latch into a series of inverters. Can I do that? Just for sake of understanding. We know that N1 equal to N3 equal to N5 and all that. We know this. So what happens now? It means that if N1 was given a positive noise, then N3 also is given a positive noise, and N5 also is given a positive noise. And same applies for N2, N4, and N6. That will be the worst case. Am I right?
Yes, sir.
Now, if we plot the butterfly curve now, see, this will be N1, N3, N5, this will be N2, N4, N6, and so on. In this butterfly curve, let me say I injected noise onto N1. So N1 pe, on this axis, I injected a noise here. So when N1 was 0, this particular curve was being followed. Are you with me? So I injected a noise. What happened? N2 became slightly lower than 0. Slightly lower than 1. On N2, I injected the opposite side of noise. So what happened? When N2 went to further lower value, N1 became slightly greater than 0. Now on N3, I inject that noise again. When I inject noise on N3, N2 comes here. So initially it was here, now it has come here. I inject noise on N4. And you will see that there will come a point when they will just move between this. I cannot go any further because in4 भी यहीं पे है. In4 में noise डाला तो I am just stuck in this loop here. Are you able to see this? So it means that my circuit is safe for this amount of noise. If this amount of noise comes, then I stored 0 on N1. Okay, that 0 will go to this value. And I had stored 1 on N2, that 1 would go to slightly lower than that. But I will still have 0 and 1. Are you able to see this? Any questions?
So the point that where they will converge, like they will start repeating each other, is our noise margin. कितना आप दे सकते हो?
अभी मैं वहां नहीं आया. मैं तो ये बता रहा हूँ, this noise, the circuit is stable.
Okay, okay.
Noise margin will come at.
Yes,
But
yes.
this noise, it is not getting troubled. This noise is safe.
Yes, sir.
This noise is definitely less than the noise margin that we could think of. I have more noise margin than this noise. This much I can say.
Yes, sir.
Now let's increase the amount of noise. Let us say I put in that much of noise. So then in the next cycle, what happens to N2? N2 would put this kind of noise. So N1 has now come here. Now again, I will put noise on this. N2 will come here. Again, I will put, now N4 will come there. In 4 I will now put a noise. So it will go on to this curve. You see, N5 is almost close to VDD by 2 now. But I have to inject noise on N5. As soon as I injected noise on N5, what happened? My N5 was almost, now it was already close to VDD by 2. It has now grown beyond VDD by 2. And my N6 is now almost 0. It was meant to be 1, but it is almost 0. The next noise, and I am fully at 0. I have completely flipped. So for this value of noise, my circuit is not stable. So noise margin is somewhere between the first case and this case. Are you able to see this?
Yes, sir.
So what is that? What is that unique case which we would call as noise margin? So that unique case would appear something like this. Okay, I put some noise there, and here. Now this is the largest square that I can fit into these lobes. If there are two asymmetrical lobes, then the smaller square is the noise margin. Because I have shown you symmetrical lobes, the noise margin on both the sides is same. But you can come across cells where the lobes are asymmetrical. So you may say this is the noise margin. No, this is the noise margin. Because if this was the data that you were storing, only this amount of noise could toggle it into the other side. Are you able to see this? So for memories or for latches, people will talk about butterfly curves. So you should now be able to answer what a butterfly curve is. And when they talk about stability or noise margin, you should be able to tell that the stability can be measured by fitting the largest square in the smaller lobe of the butterfly curve. Is this thing clear? Any questions?
Sir,